electricity through the heart. Did everybody get the message I sent on Canvas? Okay. I do apologize because I don't like to alter slides as much as possible, but I just, as I was going through it, I did not like the way it was structured. So I just altered a couple of slides. I sent them in the message, just the new slides themselves. So if you've already downloaded the deck, you can just download that and throw them in there. I also added the whole PDF, and then everything on Canvas, the main page, is updated as well with the new material. So it's not additional stuff. It's just phrased and structured in a way I think makes more sense to you all. I hope, at least, all right? So I will do my best to refrain from adjusting slides mid-game, but in this case I think it's going to be the risk benefit is on our side, all right? So this is today is a good example of a lot of slides in number, but in material there's a lot of repeats. So we're going to see this action potential slide like 10 times. We're going to see the same material over and over again to reinforce it. And if anybody's prefaced these slides, look through them already, it looks like today can be a jumble of ions flowing this way and that, what's happening when and what. We're gonna do a good baseline, make it as simple as we can, because that's really all we need to be. You could teach an entire course, I could teach an entire course on just what happens during the cardiac cycle. So we're gonna focus on the basics. But hopefully what happens here is you form the baseline understanding of why fluids and electrolytes are so important, electrolyte imbalances are so important as you move forward into subsequent clinical courses, right? Really, what happens when we have alterations of potassium balance, calcium balance, sodium balance is not what really affects the skeletal muscles or anything else, but what really affects the cardiac myocytes. That's what the real danger is. And you'll start to see that and understand that as we walk through this, okay? Do I have any questions to begin the day with? All right. So does everybody know what electricity is? I love this slide because it explains what electricity is. Does everybody know what it is? Good. All right. So next slide. In the body, we have what's called the law of electroneutrality. So we don't walk around charged. We walk around at a net zero. All right. When you'll discuss that more in biochemistry, referring to the overall pluses and minuses and the chemical equations that balance those. On our end, what we worry about is there are membrane potentials. So potentials across like cell membranes, which we'll talk a lot about today. So just because everything is a net zero doesn't mean there are differences in charges, pluses and minuses, throughout the body scattered. Does that make sense? But the whole thing, if you just took the whole ball of pluses and minuses, they equal zero. But like for the heart right now, everybody's heart is beating, I hope, right? So pluses and minuses are moving back and forth against membrane potentials, which is what we're discussing today. So understand that. And if you look at this, this is just a conceptualization. You don't have to worry about the ions on here, what they mean at this point. This is just to say that there is a constant movement of a positive ion or a negative ion into or out of the cell, which ultimately is what is responsible for our depolarization and our repolarization of cardiac myocytes, okay? Electrical potential, everybody understands that. If it's more positive on one side, more negative on the other side, things will have a tendency to move across to try to attain homeostasis, electroneutrality, right? And that's the very principle of what we're going to be talking about today. Chemical potential as well. So chemical potential really, what is another word for how that is described? Electrolytes will tend to equalize on either side of a membrane. Diffusion. It's diffusion, simply, right? Right? We'll attempt to equalize on either side of a semi-permeable membrane, right? Something goes from high concentration to low concentration until the concentrations are equal across the semi-permeable membrane, right? That is essentially diffusion. And then when you get, I think, A&P I, we'll talk more about this, so biochemistry, about the process of active diffusion, moving things across gradients, against gradients, things like that. But just suffice it to say, that's diffusion, put simply, okay? How do these things, what are the doorways that these things use to move across these membranes, across the cell membrane? If you see plasma membrane or cell membrane, again, we're talking about the same thing, right? Plasma membrane and cell membrane are interchangeable. But leakage channels, exactly what they sound like. Things leak through, always open. It's like an open door, okay? Voltage gated, what does it sound like? It's gated when a certain threshold of positive or negative is met, that gate opens and ions are allowed to go through. We're going to talk about those a lot today. Mechanically gated is exactly like pressure, temperature, force, something like that, distorts the channel and opens it and allows things to pass through. Does anybody know what commotio cordis is? Commotio cordis is what happens when a force is applied to the chest in a mechanically gated ATP potassium channel is forced open, allowing potassium into the heart musculature at the exact right moment of the T wave upslope and causes ventricular fibrillation, which is also how you kill somebody with potassium and lethal injection. Because what it does is at that right exact moment, the potassium influx into the cell prevents repolarization, and then you get ventricular fibrillation, right? Which is not a perfusing rhythm, right? Remember the, what was the guy's name? What was the Bills player who just happened to? DeMar Hamlin, yeah. It also happened to a Blues hockey player. Hockey plug, right to the chest. Blammo. So, anyway, that's what a mechanically gated, just a little interesting fact there. Ligand gated, we're going to talk about a lot when we talk about the endocrine. Some kind of neurotransmitter attaches to a receptor. That receptor opens or closes something to allow movement into or out of the cell. All right? Just a once over the world of what all these things mean. And there, for those of you who are visual learners, is what they look like. Okay? They're not that big in real life, though. So, electricity in the body. So, everybody's familiar with what an EKG is. It's a readout of the electrical energy of the heart. That electrical energy is representative of depolarization and repolarization of the various chambers of the heart. Okay? What that is electrically voltage-gated channels opening, closing to allow movement of ions into or out of the myocytes to make something happen. And that something is an electrical propagation of a signal, an action potential through the heart musculature to make it squeeze. They squeeze blood out to keep us alive, right? That's essentially what that is. So depolarization is, you see the phrasing here where it says less negative and more negative. The reason why it's phrased that way is because the stable, for a cardiac myocyte, the working cells that actually squeeze, all right, not the ones that conduct electricity, but the ones who receive it and actually squeeze together, its stable resting potential is a net negative. It's about negative 90, if I remember right, or negative 60. Doesn't matter. It's negative, right? Numbers don't really matter to me all that much, by the way. So it's net negative. And what happens is positive ions flow through to bring that negativity up to a more positive, and then we get fire. Okay? So that's why it's written that way, which sounds confusing instead of less negative instead of saying more positive. And then if you want to think about this, depolarization is squeezing, right? Firing. Repolarization, you can think of it as relaxing, right? Just general terminology, I told you I was going to define terms. These seem simple, but I want to make sure that everybody understands what they mean. Influx of an ion means it's going into the cell. It's going from the outside through the plasma membrane into the cytosol, into the cell itself. Right? Efflux is the opposite. It's moving out. Okay? So, if you want to look at this, this is not representative of a cardiac myocyte. What it is representative of is a cell somewhere in the body. You guys probably don't know this yet, but sodium is our major extracellular cation. And what's a cation? A positively charged ion. Exactly. Chlorides are our major extracellular anion, and potassium is our major intracellular cation. All right? And the movement of potassium and sodium across these voltage-gated channels is what is going to initiate our depolarization. Okay? moving that threshold, right? Because see what we have here? A net negative, little bit positive on the outside, right? So as the sodium moves this way rapidly, what happens to this charge? Charge on the inside of the cell starts to go from negative to less negative, almost to positive, right? So stick with me on that. Now looking at this slide. I told you today's going to be redundant. And it's going to be. You're going to see this slide like 5 times. Here's the deal. Despite all of the slides, this slide is going to be broken out into about 15 slides. If you understand this and this, that is everything in those slides. Okay? So let's go through it real fast. Explain the difference. And I know we haven't, this is a prelude, because I'm going to go over this in excruciating detail in a minute, but let's go over it now. Okay? So, sinoatrial node. What is the sinoatrial node? Just what is it? The pacemaker. It's a conductive cell in the heart, right? It has just exactly that, a pacemaker potential. So you see how, look at the contractile myocardium, the one on your right. You see how there's a flat level 4, or phase 4, right? And you see how there's no flat area on the sinoatrial node one, right? That's because it doesn't have a resting potential. It is a pacemaker. It has what's called a pacemaker potential. It's got autoarrhythmic, so it fires on its own, okay? That's why there's no stable flat line. You see what happens? Why does it start with phase 4? Because that's what's leading into the depolarization phase. So, the colors on the graph represent the ions that are flowing in or out, all right? So we start with slow influx of sodium. We're starting with the sinoatrial node, right? And what did I say? What is the net charge on the inside of the cell before any of this happens? Negative, right? So if we start to have positive ion influx, 1 plus here, sodium, ion, 1 extra photon, what happens as it starts to flow in? It starts to slowly become less negative, right? And then blammo, calcium, 2 plus, 2 extra photons, double the positive charge, flows in really fast. What happens? Depolarization. That calcium interacts with the actin-myosin, blammo, right? Then you see that calcium is slowly leaking out the whole time. Doesn't counterbalance equally, right? It doesn't make it to a net zero. It just starts to reduce the positivity inside the cell. And then we return back to sodium flowing back in. So that's repolarization as calcium flows out, right? So if anybody wants to ask, what happened to the calcium? It gets used by the actin and myosin to fire and squeeze together. So as the potassium flows out, calcium's gone. Now we return back to a negative, then sodium starts to flow back in, all right? If that doesn't make sense now, stick with me. But does it kind of make sense conceptually? A little bit. It's all right. It's okay. We're going to talk through it over and over. Trust me. On the other side, the contractile myocardium, the muscles that move, right? The muscle cells that move. We have a refractory period, right? So we have a period of delay. I'll just give you a hint. That delay period allows proper propagation through all of the myocytes. Because remember, this has to be an organized rhythm that fires together. We can't have individual cells firing one after another. Cardiac myocytes have to essentially depolarize all together. And we'll talk about that. That's not exactly 100% true. But we're dealing in fractions of microseconds, fractions of milliseconds, I should say, which is like an instant, faster than you can snap your fingers. So think about it as instantaneous, simultaneous depolarization. All right. Anyway, so see all the big arrows? In this case, we have a faster influx of sodium, leads to depolarization. We have a brief period where we have sort of a brief repolarization, okay, where potassium is flowing out. So it sort of almost balances because Na plus, K plus, 1 proton, sort of balances out, brings it back to a resting potential. Almost, not really, not. But plateau phase, that allows everything to deploy together. And then repolarization. So it's similar as far as the ion inflow and outflow It's just on the sinoatrial side, like the conductive side. The main driver of this depolarization is calcium. On this side, the main driver of depolarization is sodium. That is several mouthfuls. But does everybody sort of follow along right now? Not really? Fine. We're going to do it in more detail. Okay? Any questions about that stuff? That is a prelude to the whole rest of the class, by the way. If you can understand that slide like that, that's it. That's this entire day. Okay? And hopefully by the end of the day you can. So, cardiac muscle cells, also known as cardiomyocytes. I told you everything has to have 4 names. Here's the thing to remember about this. All of it. Sinoatrial cells, the conductive cells, AV bundle, Purkinje fibers, they are all cardiomyocytes. There is not a nerve tract within the heart. The muscles are depolarizing from the propagation of the active potential from one cell to the next. The difference between, SA node, AV node cells, and the working cells is sort of the structure of them, okay? So we'll go over that a little bit. Just understand, when you look at and I'll show you in the diagrams even I have here. When you look at the diagrams, what does yellow usually mean on an anatomy drawing? Nerve, right? Usually means it's a nerve. This is not a nerve propagation. It's initiated by the sympathetic or parasympathetic nerve because there is nerve innervation of the SA node of the heart. But that actual propagation of the signal that causes the squeeze is all through muscle cells. Okay? Make sense? So, shorter muscle cells, shorter than muscle cells. Have you guys gone over muscle cells yet? At all? All right, well, that's okay. We're going to fill in the blanks. Just, they're shorter than muscle cells. We'll stick with that, right? And they have unique features that help that propagation of that signal travel so that it is almost instantaneous from one to the next. All right? So, nuclei, who cares? Here's what we care about. They're organized at the end. So what is a sarcolemma? Does anybody know what a sarcomere is? All right, let's bring everybody together. Hold on, I'm going to show you. This thing right here. And I don't know if I added that or not. Sarcomere is an individual unit of contraction of the muscle, right? It's made up of actin and myosin, thick and thin filaments that move against each other and cause contraction, okay? So, the way the working cardiomyocyte is, it's organized into these nice bundles like this, right? You can see sort of the bands across. This is pacemaker cell, so an SA node cell. It's still a myocyte. It just doesn't look like that. It's longer, skinnier. It's not organized into these sarcomeres or these active units, right? I don't care in this class about actin and myosin and all that stuff. I just wanted to show you what the sarcomere looks like. So essentially, when these depolarize, they squeeze together. They bring the filaments together like that, and then they relax and come back apart, all right? So that's what a sarcomere is. It's a working unit of a muscle cell. And this is still a muscle cell, even though it's not a skeletal muscle cell. Let me go back. So that sarcolemma is the membrane that surrounds a muscle cell. That's all it is, right? That's why I wanted to explain what a sarcomere is. Intercalated disc. So think about like a wave. Think about how like someone like plugged together. Let me show you. Might make it easier to show you what I'm talking about. But it's the connections between the individual units. It's a connection between the individual cells. So the intercalated discs are this guy right here, just a sort of wavy connection that sort of stair steps and connects one cell, one sarcomere to the next. Right? So it's just the way it's connected. All right, where it's connected, I should say. What physically holds them together are these things called desmosomes, all right? That physically glues them together, if you want to think about it that way. But the important thing, the most important thing on this slide, is what's called a gap junction. What does it sound like a gap junction is? A portal between the two cells. It's a gap at the junction. It's exactly what it is. It is literally a gap at the junction that allows the propagation of that electricity to fly through the muscle cells from one to the next. So that's what really helps contribute to the organized depolarization and contraction. Does that make sense? So, these gap junctions right here, literally, I know, this is a representation, of course, but they're holes, they're gaps at the junctions. Think about that as where the electricity flies through from one to the next, allowing the cells to depolarize together, not individually one to the next. Because what would happen if cardiomyocytes deployed one at a time, or in succession? You'd have an extraordinarily disorganized rhythm. It'd be chaos, right? We need this to fire all together. And that's what allows this to happen, all right? Have you guys covered mitochondria yet? Does anybody not know what a mitochondria is? Well, let me just explain what a mitochondria is. It's the energy, the powerhouse of the cell, is how it's always described. The energy unit that has the enzymes that create the ATP that allow for the energy of the cell, right? Does it stand to reason to you that there are more mitochondria in a cardiac cell than in a skeletal muscle cell? And why? Does your heart ever get a chance to rest? Exactly. And that's why there's more mitochondria in cardiac muscle cells. Because it needs more energy, because it's always on, right? When you're sleeping, your skeletal muscles, unless you're old and decrepit like me and you have to move all the time, are generally at rest. So you don't need a lot of mitochondria. They get a chance to recover and recuperate. Your heart still has to be beating, right? Even though it's beating slowly, more slowly, it's still going. That's why there's more mitochondria, more powerhouses per unit, all right? This is just another picture. It sort of helps you, I think, a little bit better understand these desmosomes, which are the things that sort of hold the cells together. The gap junctions are literally, like, again, a portal from one cell to the next. And the white wavy line represents the intercalated discs, where the cells plug in from one to the next. Is that simple enough? Okay. And then back to this one. Again, just looking at what an organized sarcomere is in a cardiomyocyte, and then just the visual representation of the difference between the cells. But again, the important thing to understand is that they're both muscle cells. One is just a specialized type of cardiac muscle cell, the other is just the regular one. All right? Fair enough? Am I going too fast? You guys good? Okay. All right, so this is the mitochondria slide. Same thing, just it takes up more of the cytosolic space. You guys know what the cytosol is? It's the goo inside the cell. Yep. So within that, a muscle cell doesn't look like your typical, we've all had biology, we draw a cell, we draw a circle with stuff inside of it. Muscle cell doesn't look like that, but the cytoplasmic space, the cytosol, is still there, filled with these organelles, and in this case, we have a lot more power-generating organelles, right? Because we need to have more, because of what the heart does, okay? Now, starting to delineate. Two types we talked about, autorhythmic or conductive cells. What does the term autorhythmic mean to you? It means automatic rhythm, exactly. And you remember seeing that graph of the sinoatrial nerve, the one on the left. It doesn't have a baseline. It doesn't have a baseline. I said it had a pacemaker potential. This is why. It's an autorhythmic cell. It just keeps going, keeps going, keeps going, all right? So no rest period, no phase 4. And then we have the actual musculature, like what you would think of more typically as a cardiomyocyte, like a working cell. We call them the contractile fibers. You'll also hear them called the working myocytes, all right? This general concept is something we've already covered. The big takeaway is this one right here, that it's not a nerve tract, right? It's conduction of electricity through cell-to-cell contact. And what facilitates that cell-to-cell contact? That propagation? The gap junction. Exactly, the gap junction, right? Okay? And again, all the way back to day 1. This is one of the reasons why there's no interstitial space between the myocytes, right? There's no cellular space between the myocytes. There's no interstitial fluid. They are held together by those intercalated discs, physically held together by the desmosomes so that we can get bam, bam, bam. So if you put a battery or an electric charge on a heart that's freshly dead, it will still all together at the same time, right? It'll propagate because it doesn't need a nerve, it just needs a signal. All right, does that make sense? All right. So that's why we don't have any interstitial space, because we don't have time, literally, and I mean time literally in this, we don't have time, we're talking about fractions of milliseconds, to travel from a cell through a space to another cell. We have to depolarize as a human, all right? You got this video. It might help you conceptualize if you want to watch it on your own, but it's just going to go through everything that I say right now. So I put them in there so that you can use them at your leisure if you want to, okay? So this is what you would call a very simplified representation of the propagation of an action potential. So pacemaker cell, where's that going to be? The SA node, right? Excuse me. Right through, what is this? What does this look at? Yeah, junction. Right? And then blammo. And when I say blammo, I mean depolarization. All right? Exactly. It just flows right through. Connected, connected, connected. Doesn't have to go through any interstitial space. All right, back to this. Prelude into, but does it make sense a little bit? Because what's really the signal is the electricity. Electricity is causing this to happen within cell to cell, right? So the electrical message is happening as it propagates from one to the next, but this is what's happening in the individual cell, right? And again, depolarizing altogether. So here we go. Just another visualization of it. And again, if you go back here, just to look at this one. So SA node cells, they are shaped weird. There's elongated ones we'll talk about, which are part of like Bachman bundle. There's Purkinje fibers, which are longer, fibrous, like elongated, like cardiomyocytes that function as electrical conductors. And then we have the round, sort of the SA node does have some of these more rounded, like ovoid shaped cells. Just a visual representation, all right? Just, you know, the takeaway, the reason why I'm harping on it is to understand that they are still the same cell. They're myocytes, just their shape and function different, right? They're not nerve cells, okay? Okay, so this is a good representation of what I was talking about. Yellow, and this, like, if you looked at yellow, you would, you know, and you didn't have the knowledge, you would just say, hey, those are nerves running through the heart. But what they are, what the yellow represents, are the conductive cells, the conductive cardiomyocytes. All right, and if you just want to take it through this drawing real fast, the sinoatrial node is right here. Remember we talked about yesterday? It's in the right atrium. Okay. And then these other fibers, these internodal pathways, represents what's called Bachman's bundle. Right? Internodal pathways. And what do? They depolarize the atria. See where they are? So the atria have to depolarize simultaneously too. So we have one that fills up this space over here, and one that goes over to the left atrium and depolarizes it, because the atria fire simultaneously. And then the bundle of His, otherwise known as what? Anybody remember? Oh no, sorry. The atrioventricular node. Okay? And what is this green? Represents a delay. Okay? And why do we need to, we're going to get to all this again, but I want to like thought problem this together. Why do we need a delay right there? After the atria fire, why do we need to slow it down just a little bit? Exactly. To let the ventricles fill up before they squeeze, or else we're not going to get sufficient blood flow into the ventricles, and we're going to have a reduced cardiac output because we're not squeezing enough blood out. So we slow it down because we're in ventricular diastole to let the ventricles fill up, and then it goes down through the bundle of His, which is another name for what? Anybody? The A-B bundle? Yeah, the A-B bundle. And what does the A-B bundle go through to make sure that the atria and ventricle don't depolarize simultaneously? Close. The fibrous skeleton. The fibrous skeleton. Remember that blue thing in the picture? That's right. It also connects. It's right on top between the atria and the ventricles, and it acts as an insulator so that all the energy doesn't go through all of the cells. Because now we see, if that wasn't there, because of the conduction velocity, if there was no insulation between the atria and the ventricles, we would have a full heart squeeze as soon as that depolarization happened within the SA node. Does that make sense? Okay, so we have that fibroskeleton as an insulator, but then once it gets through there, it's game on, down through the bundle of branches, not the bundle of branches, the bundle of branches, and then up through the Purkinje fibers. And we have ventricular squeeze. All right? Again, if you understand that, that's the remainder of today. Does that make sense? Because we're gonna talk about every one of those steps individually. But does that make sense? All right. So, we've already covered this. The conductive cells, the autorhythmic cells, specialized myocytes, still muscle cells, just different, have autorhythmicity, which means they're self-excitable, which means they have no resting membrane potential, they have a pacemaker potential. All right? And this is what I was talking about. If you get a freshly dead heart, or the tissue hasn't necrosed yet, and you zap it with electricity, it'll fire. Okay? So, most of the cardiomyocytes, as you can imagine, are working muscle cells that squeeze blood out of it. So the vast majority are that. It doesn't matter 1%, 10%, who cares? There are many, many fewer autorhythmic cells than there are working cardiomyocytes. All right? And pacemaker potential. Okay. What is an action potential that I've been referring to? Action potential is essentially that threshold of change of positive and negative that causes and leads to depolarization. All right. So the SA node, through its innervation of either the parasympathetic or the sympathetic nervous system, both, has an inherent rate of firing of action potential production. Okay? Does anybody want to hazard a guess what the action potential production of the SA node is? 60 to 100. Yeah. 60 to about 100. Normal resting heart rate. Normal heart rate, right? You guys don't learn normal. 60 to 100. That is it, because that's what happens. As the SA node fires at that speed, that's what causes our heart rate. As it increases, for reasons which we'll talk about tomorrow, or decreases, and we go either on outside. But anyway, it's setting the pace, right? But that's its inherent rate of firing, 60 to 80, which is, or 60 to 100, excuse me. Okay? And then we talked about this. Depolarization is contraction, and then the easy way to remember it is repolarization is relaxation or recovery, however you want to remember it. Again, little memory tricks sometimes help when you have a lot of shit to remember, right? And there you go. SA node initiates an action potential every 0.6 to 1 seconds, which equals 60 to 100, right? We got it. And these numbers right here, don't worry about that, okay? What happens, what the takeaway of that is parasympathetic. What is the colloquialism for parasympathetic? Rest, digest, feed, or breathe, whatever, slow down, right? We're gonna sit down, we're gonna digest the antelope, right? So that will slow our heart rate down. Does anybody want to take a guess what nerve is responsible for that? The vagus. Yeah, there you go. Cranial nerve 10, the vagus nerve, all right? And then, so on the other side, we have fight or flight. We gotta run away from the lion. Need heart rate to go faster, so we supply more blood to our skeletal muscle so we can run and not die. Now, goes up through cardiac accelerator nerves, again, we'll talk about tomorrow, okay? Okay, now, this is where we start propagation of action potential. We are all together in the SA node in the upper right atrium, right? That's where we start, that's the heart's natural pacemaker. So this is where it is. just by the vena cava. Okay. And no stable resting potential. Is that clear at this point? These are the conductive cells. They just keep going, right? Now, SA node, I have it labeled here as 1 because this is where the propagation will begin. Okay. Right here, and then it starts down. These white arrows are what happens as soon as it leaves the SA node. It goes down to the internodal pathways. What does internodal mean to you? Between nodes, literally between the SA and AV nodes. All right? And then we have our friend Bachman's bundle, which goes through to the other atrium. All right? So what does that cause? When that nerve propagation goes, see, I said it. When that electrical propagation goes through the 2 atria, what does that cause? Atrial systole. Simultaneous, organized atrial systole. Exactly, atrial contraction, right? Does that make sense? And that's how we got to start, all right? So that's why I didn't put a 2 on Bachman's bundle. Because when the SA node fires, it goes through those internodal pathways. That's kind of a 1A, 1B situation. Does that make sense? Okay. And again, you don't have to, this is just another visual representation. I don't really care that you know that the stable, or that the bottom end of the transmembrane potential is negative 60 millivolts. I just need you to know that it continues to fire over and over again, and that there is no flat baseline. All right, there's no stable resting membrane potential. And if you look, we just put let me go back to the laser plate here. So we have last part of the previous one, right? Let's start right here. So we have sodium, 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 right? 1 plus, then 2 plus, and then contraction, and then now we're losing potassium to drop back down to negative, and we just do the whole thing over again. All right? Make more sense on this one, maybe. Slow input of potassium, or sodium, slowly bringing to a less negative state. Fast input of calcium, which is 2 plus. Efflux of potassium, which brings us back down to net negative. Sodium starts to come back in, calcium starts to come back. Then it just does it over and over and over again. Does that make sense? Everybody? All right.
So what's more important to know in this situation? Just that it's depolarizing or repolarizing, or the actual amount of?
Not the amount of anything. What the ion movement is crucial to understand, right? You have to understand the ion movement and what's causing what phase of happen. But again, it's only 3 things, right? It's sodium coming in slowly, calcium coming in fast, leaking out through the leakage channels of potassium, and then and then repeat, rinse and repeat over and over. Yeah.
When you say 1A and 1B, what exactly were you?
Oh, I was talking about back here. I was talking about, because I have the SA node labeled as number 1 right there next to it, but I didn't put Bachman's bundle as number 2. It's just because it really goes bam, bam. You know what I mean? So 1A, 1B. It doesn't really have a delay across here. It has a delay down when you get to the AV node, which is where we're going to see our number 2. Does that make sense?
Yes.
What's up?
I'm just curious, when is the influx of potassium? Because it's always talking about leakage and rapid efflux.
Uh-huh.
At what point is it influx?
It starts to influx. If you look at that, go back to this one. It starts to influx. It's kind of, truthfully, potassium is always sort of leaking in. You know, especially when you have this one that doesn't have that has automaticity. So it's, as potassium dives in fast, we're still leaking potassium, so it kind of then allows it to drive back down to a net negative, and then so it's always sort of overlapping a little bit. Does that make sense? Does it make sense to you guys? Because again, we're slowly bringing in sodium, then we're dumping in a ton of a 2+ ion. So we still have to keep it stabilized, it still has to drop back down, or else there won't be another resting member of potential. And this outflow, consistent outflow of potassium is really why it has automaticity. Because it's constantly returning itself back to a negative, and then bam, when it gets positive. See, does that make sense? Yes. Okay. Does that make sense to everybody? Okay. Where the hell was I? Oh, was I here? No, I was way past there. Yes, sir. Ma'am.
Someone that's on like calcium channel blockers,
Uh-huh.
you see that maximum potential being lower.
Yeah, it can be. There's two. We have the the hydropyridines, the dihydropyridines, and non-dihydropyridines. So two different ways. If I remember right, the non-dihydropyridines work more in like the vasculature, because this same mechanism happens within the vasculature to a certain extent. And then the dihydropyridines can block calcium channels to sort of slow down the heart rate and slow down the contractility to a certain extent, which helps us reduce systemic blood pressure. So yeah, basically, yeah. But again, it doesn't block it. It doesn't block it, or else the whole shit show stops. You know what I mean? Which is why calcium is bad. Which is another reason why, and this is going way off topic, when you're stabilizing the cardiac myocytes, when you have like a severe hyperglycemia, like a diabetic ketoacidosis, before you give insulin to somebody, you got to stabilize their cardiac musculature with calcium first before you give them the potassium. Otherwise, you're going to send them into hyperkalemia and kill them. So, all right. Where was it? Here. Okay, here. So, Bachman's bundle. All right. Now, I'm going to go back. I labeled anterior. Right, a labeled anterior internodal pathway. But what would give it away that you see in this picture that would tell you that that one is the anterior versus the other one that's posterior? Huh?
The bicuspid versus tricuspid.
No, you're all getting close. What? It's smooth, exactly. Smooth anterior wall, rough posterior wall. Pectinate muscles, right? Exactly. What's this little oval-shaped dent? Fossa ovalis. That used to be the foramen ovale. Man, you guys know some shit. All right. I like it. So, anterior, smooth wall, right? Smooth anterior wall of the right atrium, rough posterior wall where the pectinate muscles are, okay? What's the dividing line? Crista terminalis, terminal crest. You got it, right? So this has no delay, right? There's no fibroskeleton that goes to insulate between the atria because we need that energy to fire fast. So this is why I was saying 1 and 1A, right? That's what I was talking about. Does that make sense? Okay. Simultaneous atrial contraction because of the propagation through that. Okay? Now we go down to the AV node where we slow down. All right? The atrioventricular node. Closer to the septum, an anteraatrial septum. Has its own action potential, inherent firing rate. Those of you who have had ACLS in the past probably know that it has its own inherent rate. If we lose the SA node, we don't lose the heart, we just slow it down because now what's pacing the heart is the AV node. All right? From the AV node, actually, this is it, right? This is what we talked about. What's the reason for the slow conduction? Gotta let the blood get into the ventricle, okay? All right. And that's why the inherent firing rate of the AV node is slower. Okay, because the conductive tissue is slower, more insulated, so it doesn't fly through there so fast. Now, in the AV bundle of his, now we got to speed back up, right? So we have super fast firing across the atrium, down to the AV node where it slows down. And now we got to speed back up because that electricity has to make its way all the way down and around to the upper outside. All of the myocardium of the ventricles, which are larger chambers, and have more myocardium. Does that make sense? So we got to speed up, right? Atrioventricular node, number 2. AV bundle of his, number 3. Okay. AV bundle splits into the bundle branches. You've heard of, I'm sure at this point, you've heard of the right and left bundle branches. Okay? Down through the bundle branches, and then at the bottom, which is the apex, remember, right? They change, or split, I should say, into Purkinje fibers. And those Purkinje fibers have their tendrils all the way up to the top of the ventricular walls. So we go AV node, AV bundle, bundle branches, Purkinje fibers. So, and also this is a pretty good representation of what I was talking about yesterday. Do you see that there are those yellow lines in, what are those called? The papillary muscles. So when they contract, they prevent the eversion, right? When the whole heart contracts, they contract as well. All right? Yes, sir.
Do the Purkinje fibers go into the left ventricle and the right one, or
Yep.
just the left?
Yeah, I mean, this isn't a super great representation, but essentially all these branches are Purkinje fibers to sort of branch out and make sure the entire thickness of the myocardium is, receives the energy, right? Because again, we need the Purkinje fibers because the transmission of the signal does slow through the myocardium. So we need to make sure we have sort of as much of those conductive fibers as possible. Does that make sense?
Yes, sir. Thank you.
All right. This is where I changed it, in case you guys. This is just, velocity equals speed, fiber velocity, and the reason why we harp on this is just not necessarily, because I don't necessarily want you to know the numbers that we're going to go through as far as meters per second of propagation. What I want you to understand is where it's slow, where it's fast, and I want you to understand why it's fast here, slow here. All right, that's what I really want you to get, the overarching message, not the individual numbers, okay? So, Bachman, I didn't start with the SA node. I should add the internodal pathways. Bachman's bundle and the internodal pathways are all about 1 meter per second, so pretty fast, right? 1 meter per second. That's how fast the energy travels through those fibers. The atrial contractile fiber, just like, so the myocytes themselves, like, it slows down, again, to allow simultaneous atrial contraction. Right? That's why it slows down to about 0.5 meter per second. Now we get to the AV node, and now we're at 0.05 meters per second. That's why it says slowest, right? Why is it slow there? So we can have a relaxation, or not, so we can have ventricular filling to occur before it, boom, makes its way down into the ventricles, right? Bundle of his, bundle branches, now it's game on, right? 2 meters per second, Purkinje fibers 4 meters per second, and then the ventricular contractile fibers themselves, a little bit faster than the atrial contractile fibers, doesn't matter, they have individual numbers, no, but as it progresses from endocardium to epicardium, which is in to out, right? It slows down a little bit. Now, the entire time, you'll see 220 milliseconds, you'll see 20 through 230 milliseconds, it doesn't matter, it's fast. Almost instantaneous, right? Okay? So again, I don't care that you know those numbers. I care that you understand why those numbers are like that. All right? I'm not going to ask you how fast does it propagate through X, Y, and Z. I might ask which is the fastest or which is the slowest. That's what I want you to know. Yeah.
Does the velocity correspond with the actual size of the fibers in this case? Like, if you have bigger fibers at the base of the heart, and the SA and the AV node, and then it gets really smaller in order to propagate that.
I mean, not necessarily. Because, if you get, maybe the elongation, it's a thinner sarcolemma, more gap junctions will have propagation faster, but not necessarily the size of the cell, yeah. But yeah, kind of. That's a bullshit answer, isn't it? All right, let's see. Let's take a mental break and we'll talk about this thing, all right? Yes, ma'am. Okay. Okay. Yes, we're gonna talk about more about what's happening. So this is the innovative. Five is part of it. So all of your that's gonna pick it up, slow it down. So yeah, there is an initiation of nerve impulse that starts this whole thing to go. But the important thing we're talking about is like, just to understand that nerve tracks at the innovation is there is points of activation. What we're talking about now, the induction of that signal isn't through like a neuron and then it's
Depolarization.
the innovation. So we have to what is the genesis of that? I don't want to talk about nervous systems. I don't want here's innovation.
I think I'm gonna have to practice right out probably at what point is calcium coming in and when it will spike potassium. Things are starting to come back to me, I'm remembering how much I didn't like this.
What I'm saying is, so this one doesn't have to actually have a mass influx.
Got my,
Look at every
Poured out right here.
massive leak. It's always leaking. But what I'm saying is that this is always firing.
We are it's not just flowing in.
Bing.
That's it. There's no like, oh, this is where everything.
You might have, we were saying joking language. It gets to we'll talk about it more.
So that's,
Exactly.
so because it's so constant, you say that for our purposes, okay, I get what you're doing.
Isn't that crazy years ago?
You know what I mean?
Yeah, like what makes me like
You know,
screwing my face with my hair. I think I should like off my body. Very like just doing stuff and strip off it.
But it just goes through the
Like usually what I've been doing is like a load so like once a day for like 2 weeks, and then I was able to like got like when back to like just 1 2 weeks. But I think it's just over time like
There, we mentioned the moderator large amount.
yeah.
It's actually, no, it's just a special.
Let's see. Environment too, because for me, work, it's cold, and it's springtime, like it's worse. I feel like forever, but like or like right here.
I might try to think about, I used to have a leader too. And I have so much energy, I'm just like, I'm just gonna. Unless it's distracting, it's distracting. No, it's not.
And also.
Yeah.
Alright. Thank you. Yeah.
It sucked, it was like.
Gosh, that's. Grinding. It's a blow. Right. No.
Things like
Well, like you wake up like, oh, that you're alone. I hate that. Like I short insulation. Always look up my lines. It's not necessarily good for
it's just the already got to bring it back.
Why is it CO2?
You bring your mattress everywhere.
Oh, I was like, I'm married. Yeah, like if
Because I go home to take a nap.
yeah, it'll be fun if you I feel like if you don't have like you don't have foundational like shit right now, that would be really hard. It's kind of hard to like just to deal with the
Fast calcium. Oh, and then fast.
Because they won't spend time with doing
I feel like it would only work if you're both wearing coat. So it's like you're able to see just everything like yeah, like well yeah, you can study together, but like let's say like you're both in two senior programs and like Saturday like leisure days, like that's when you do something else.
Right.
That could easily work. I think the thing I would see it doing is like clothing like trying to get back you know, drag out last time. Like someone else has to put like your text all day long. That's okay. Like me and my wife is like when we started dating, like we'd be like talking and texting all the time.
That's when it's more like when it started.
You see that, but then like I look back on it and I'm like now like someone's texting me all the time, like and I'm just like
That's what I need.
I really noticed you that like you know you're busy, so you know you'll call me.
yeah.
Black hair.
Oh, this one, yeah. What that? That's what gets me. And then read more.
I did.
But then this is the contraction.
You guys are gonna see.
Contraction's right at the top.
Yeah. Yeah. We have a graph folder superimposed on the net.
So like I'm trying to figure out. Because it's weird. Whenever I see something going up, I'm like, oh, it's obviously contracting. It's going up. It's getting bigger and then going down.
See that graph is the threshold of membrane charge, right? Charge is going up positive into a certain area. Bam. And then we're gonna, so we have a graph that's superimposed contractility and charge. So just stick with me for a little bit. Okay, alright, later. Alright, so again, this slide here isn't necessarily that I want you to know these numbers, okay? But what the numbers do represent, the numbers in red, are the velocity through the individual cardiomyocytes, the conductive cells, right? So we have the individual conductivity, and then the green represents the start from SA node, 0.7 seconds to the AV node, and then all the way through to where we get to, like I said, 0.23, 0.21 to the top of the ventricular myocardium, right? So that's what the green is, the propagation of the action potential through all of the cells. So it's just the reason I put it here because I think it's a good visual representation of the numbers on the previous slide. Just kind of shows you fast, slow through the AV node, and then bang, lightning, right? Does that make sense? Okay. Does anybody have any questions about this? About why the velocities are the way they are? Anything like that? Okay. Yes?
Did you say slow through the AV node?
Yep, slow through the AV node. See where it says AV node 0.05 meters per second? So that's what slows it down right there, so we can let the ventricles fill and then blend all the way down.
I forgot how numbers work for a second.
Numbers are hard, man. We can't math in the morning.
Yeah.
I understand, trust me. Don't ask me to do math up on the stage, you'll get ugly. All right. So, the rates of AP conduction, right, that is the how fast they inherently generate. We've already discussed this, that each one of the areas of the conductive cells have their own inherent rate of firing, their own pacemaker potential, okay? And so, you see that the lower end of the SA node is the upper end of the AV node, and the same with the AV node and the Purkinje fiber. Okay? So what does this mean? Why is this clinically? How is this relevant? If we have something that takes out the SA node, the heart just doesn't stop. It has another inherent pacemaker. It drops down. The AV node can perfuse the body for a while. But what do we lose if we lose the SA node? Atrium. Exactly, atrial contraction. So we have reduced ventricular filling. All right. Then, if we lose the AV node, considering where it is, what do we lose? Where is it? The septum, right? In the septum, right? The AV node down the bundle branches, we lose the septum. Then we have basically what is left is an inherent ventricular rate of about 20 beats per minute. I know it says 20 to 40, but it's going to be about 20, which is really not conducive with perfusion of the rest of the body. So the heart will continue to pump if we lose these pieces. And how do we lose them? Well, we have an SA node, an MI where the SA node is. It's gone. If we have a septal infarct, we lose the AV node or the bundle branches. They're gone. So again, the heart will continue on as much as it can. But if you're firing at 20 action potentials a minute and you're an average San Antonio resident, you're not going to be alive. So we talk about this, the rate of AP conduction, right? It correlates to our heart rate. Right? That AP conduction, 60 to 100 beats a minute, 60 to 100 action potentials a minute, translates into what we just covered, which is ventricular contraction. Right? Okay. All right, let's talk about contractile muscle cells. That was the conductive cells. Now we're going to talk about the contractile cells. We've already covered all this material, all right? But what we're going to talk about is the difference in how the action potential propagates through these guys, all right? And it is different, right? They don't have a pacemaker potential because there has to be a resting period. You guys have everybody seen an EKG, right? There's a flat piece before the next thing, right? There's got to be that flat piece, or else it's just going to be chaos, right? We're going to have just ventricular firing, not going to be filling, so we have to have a resting potential to allow it to repolarize, fill up with blood, and squeeze again. All right? Same thing with the atrial and ventricles, right? So, we're talking about the other half, the working cells now. Clear? All right. And I like this. Previous instructor is one of my favorite people ever. She said it was like the wave propagating, which is a good way to think about it. And again, how does that wave propagate? Tell me, somebody.
So it starts
What holds together the cell? The desmosomes, the intercalated disc and the desmosomes physically hold it together, and then where does the electricity travel through? You got it. That's the wave, right? And so what does that mean? It means that once the electricity hits the conductive cells,
I got a question.
Yes, sir.
So when looking at the graph, the contraction is happening.
So what you're going to see, all right, if I just had to superimpose it for you right now, what you're going to see is contraction happening like right here. Sort of like that. We have, it's coming up. I'll show you exactly when it is. But more or less what happens is when we have sufficient calcium, because calcium's what activates the actin and myosin that's squeezed together. When we have sufficient calcium in there, that's when we get a squeeze. Okay? Then we have repolarization. So what happens? No more calcium coming in. We have a mass efflux of potassium out. This sort of For anybody who's done ACLS, and for those of you who will soon, which is everybody, this is why potassium is so important in the heart, right? Because that's what causes that repolarization. Remember what I said. If you get to the right spot of the upslope of the T wave on the EKG, if you shut these gates and cause influx of potassium rather than efflux, so then you get ventricular fibrillation. All right? And again, this is not the leakage channels. This is an active pushing out of potassium to return that membrane potential down to negative, right? We used up the calcium for the actual contraction. Now we've got to squeeze out the potassium to get us back to our stable resting membrane potential, right? Which is why the graph goes down, because we're getting rid of positively charged ions, and so it's driving back down from what? From negative 10 to negative 90, right? That's why the graph is going down, because it's becoming more negative. Does that make sense, everybody? Okay. This is not something you can digest in the first pass, I understand, but just keep going, all right? And we'll talk about it again tomorrow. So, and then phase 4 is our resting membrane potential, which makes it, again, different than our SA node, AV node cells. Doesn't have automaticity. We have to have time between to have ventricular filling, and so we can have good cardiac output, so the heart can function efficiently, okay? So that's phase 4. So this represents, so again, this is sodium, right? And we have some potassium coming out here, and then calcium coming in, and this causes this, all right, which is the contraction. I know it's an oversimplification. But what is the brief repolarization allow to happen, you guys think? If that's happening before the actual, sort of at the beginning of the contraction, what do you think that little flat period at the top allows to happen? Huh?
Is that like filling up our blood?
Not filling up. What that's allowing is for the signal to propagate from the endocardium to the epicardium through the actual musculature. It allows them to fire simultaneously, all of them, right? All the way from the top of the septum down and around, and then the entire ventricle, right? And you're like, and this is what I was prefacing earlier. You're like, well, then there's a delay that doesn't sound like simultaneous contraction. Think about it. Look at the end of the end of the yellow, okay? You look at the bottom, 0 to 100. If you draw a line down, or you draw a line right in the middle. Let me just do it. So if you draw a line like right here in the middle, right? That's 50 milliseconds, all right? It's 0.005 seconds, right? Here, if you draw a line down, it's not even quite there. So we're talking about a fraction of a millisecond delay. So that's essentially instantaneous, which is why we have instantaneous contraction. Does that make sense, everybody? Physiologically, is it absolutely instantaneous? No, not necessarily, because it does have to move from one to the next, and it doesn't move at light speed. But does that make sense why it functionally is instantaneous? So I mean the reason why I explain that is because that, when I was a student, would not unwrap itself in my brain. So I just wanted to explain it to you guys. You guys probably already knew it because you're smarter than me, but I just wanted to explain what was a sticking point for me when I was trying to go over this stuff. All right? Does that make sense what I just said? All right. And then this is the long-awaited simultaneous graph, right? So once we have enough calcium, which is about where the contraction begins, right? We have enough, and then we have maximum contraction, right? So green is contraction, blue is the action potential. So like I said, they sort of overlap in that area. The other thing that is different about cardiac muscle and skeletal muscle is that you can have contraction on contraction. With skeletal muscle, you can make a harder squeeze. With a cardiomyocyte, there's an absolute refractory period, meaning that it cannot accept another action potential one on top of another, which is important because it allows for that rest period, allows the full proper depolarization, and then on to the next one. So you can't simultaneously. When you guys talk about skeletal muscle action potentials, it'll be different. All right, so you have that absolute refractory period, meaning, again, can't accept another charge. Does that make sense? When that absolute refractory period is altered because of what did we already talk about that would alter it? Commotion recorders. Potassium, hyperkalemia, extreme hyperkalemia doesn't allow for repolarization, changes what the graph looks like, and now you get contraction on contraction, and then you have ventricular fibrillation, which is what we're talking about when we talk about dysrhythmias. Okay? So again, there's got to be a period of rest, even though we think of our heart as and everything happens simultaneous. When you lengthen out that timeline and talk about it in terms of milliseconds, there are physical delays to allow everything that's supposed to happen, so that it does function as a unit. Okay? You guys good? Sorry, I know that look. That was the look when I was at PA school. Like, yeah, we're good. Thanks, Nick. All right, here's another. Again, I have a lot of different visual representations. Sometimes one picture, one graph communicates to you in a different way that makes it click, and so it's not different information. It's just presented differently. All right. And then here's our friend, the weird jellyfish guy. All right. But now, tie it all back together. Exactly what I said. We did in about 30 to 40 slides. What I said, if you can understand those two graphs, you understand what is going on. So they make a little bit more sense now on the back side of what we just explained. All right, that's all we need today, is a little bit more sense. And where conceptually it's not so off-putting, right? Then as you study it and you go through it, you come up with questions, you think about it, it starts to click, all right? It starts to click. But again, what makes the signal entry? What's the automaticity on the conductive cell side? Sort of that constant outflow of potassium, right? You see on the contractile myocardium, there's a spot where there is no potassium outflow, right? That's why it doesn't have automaticity, because it doesn't just return itself. Like it has to depolarize and do its whole thing before it can go again. All right? All right. We're almost done. Actually, we really are really close to being done. Any questions before I go to this electrocardiogram? And this is going to be the most basic concept electrocardiogram, because you have a whole EKG class and a cardiology class and an emergency medicine class where you will go over these ad infinitum. I think you were first, and I'll get, yeah. Yes, ma'am?
So it might be a dumb question.
No, it won't be. What?
I remember, because when we talk about the myocyte, that's not interstitial space.
That's correct.
So where are those ions coming from? Where those sodium, potassium, where are they flowing from?
They're still from blood, from the coronary circulation, right? That's what's feeding us our oxygen, our nutrients, our electrolytes, and taking away our waste products and taking away our carbon dioxide. It's coming from the bloodstream, right? And if you think about that, it's a good question. If we were going to measure lab, if you want to know how much potassium I have in my body right now, where are we going to measure it from? We're not going to measure the intracellular potassium. We're going to measure how much potassium I have in my serum, right? So think about it. That's the delivery system for all the tissues in the body. The blood, right? Blood is a connective tissue. You guys have heard that, I assume, before? So blood is technically a connective tissue because of that delivery. So that's where it's coming from. Okay? Does that make sense to you? All right. Yes, sir.
Mine's pretty similar, actually. I wanted to know where the sodium and the calcium go.
They're to the ether. Is that good enough?
Yeah.
They get used up. I mean, that's why you have to replenish. Like this isn't a net zero, right? We don't have a fixed amount of sodium, potassium, calcium in our system. We have to take them in exogenously, right? Whether it's through food or whether we replace it with fluids and electrolytes. But they get used up, which is suffice it to say. Is that good enough?
Yeah, I was just going to say because the potassium leaves.
Yeah. But the sodium, sodium and the calcium kind of stay. So think about it this way. Is what I was saying. the calcium is generally the culprit for muscle contractility, right? So if you have too much or too little calcium, you're gonna have either a hypertonic or a hypotonic situation. So it really is being used by the actin and myosin to fire. Okay. And that's as far as, you got to the end of, that's the end of the internet for me, man, that's all I got. All right, any other questions? All right. Okay, so, anybody have experience with EKGs? Me, good job. No, I figured, I mean, I'm sure there's a lot of extensive experience in here, but again, we're not trying to go over what vector lead does what or shows you what. We're not reading 12 leads or even 3 leads in here. It makes a point about the electricity that we just talked about and why it's represented the way it is on an EKG, all right? So, you have your limb leads, which you have your right arm, and your left arm, and your left leg. And they are not ironically titled. That is exactly where you put the little sticky thing. Okay? You can put them in different places, but generally that's where you put them, right? Then you have what's called your precordial leads. The V, in case you're wondering, stands for vector. The energy vector that you read on the EKG, right? So V1 through V6 are your precordial or chest leads, you might also see them called. And that, again, just reads energy in a different plane, in a different vector, and allows us to understand what's going on in the heart and where and why, all right? So, again, yeah, as the electricity moves, it's recorded on the EKG. So if you're seeing the waves, you're seeing electricity. As you're seeing the flat spots, you're seeing a general, like a relaxation period, all right? Anybody's ever seen a slow EKG, there's a lot more flat line. A fast EKG, there's a lot more up and down, right? That's, again, basic, okay? So, P wave, let me go back, let me do this actually. So the P wave, which is this little guy right here, the green one, is atrial depolarization, all right? And what does that mean? Yeah, okay? Then you have the QRS complex, which is this guy right here, the big part everybody knows, which is ventricular depolarization. Starting ventricular depolarization at the Q wave and ending ventricular depolarization right here. All right, and then this is the beginning of ventricular repolarization, and this is actual ventricular repolarization. All right? So there's activity on the EKG that shows you when the ventricle is relaxing and filling. Now, I'm going to go back over that, but why do you think you don't see a wave on here for atrial repolarization? Because it's hidden in the QRS, exactly. Because the atria are repolarizing when the ventricles are depolarizing. And the electricity of those huge muscular chambers is going to bury and hide the electricity of those two little sad little top guys, right? In the little ears. Alright? Okay. So, go back. This is, like I said, atrial depolarization, ventricle depolarization, and ventricular repolarization. Okay? PQRST. Why does it start with A? Because nothing can be easy, right? All right. Q wave, the QRS complex of the Q wave, just so you guys know a little bit. If you have what's called a pathologic Q wave, which means it dives down too deep, that can be evidence of an old myocardial infarction and the scar tissue that you were referring to yesterday. Energy doesn't flow through it correctly, so you have a Q wave, which is this little orange guy that dives down a little bit too deep. Sometimes, depending on the person, you might not even see much of a negative deflection at all for the QRS complex. So, if you see one, just to put this in your brains for future reference, if you see one that's a little bit too deep, this patient may have an old myocardial infarction, all right? You'd be surprised how many people out there are walking around have a little minor silent MI they don't even know about. So, and we go back, talk about waves, right? We have waves, and then we have segments, and then we have intervals. Intervals are generally between one wave and another. Segments are a wave and a flat part, and then the wave itself is obviously the deflection of the needle on the paper, okay? So, PR interval, that's the P wave, right? Atrial depolarization to the beginning of ventricular depolarization. What does that mean? The P wave to the flat part, to the deflection, bam. Then that's ventricular depolarization, okay? ST segment, important for MIs as well, but I'm not gonna overload you with them. You know, if it's high, if it's low, depending on the energy, it could be an MI, all right? Myocardial infarction, heart attack. And it represents when the ventricles are done depolarizing to when they're repolarizing. And then the QT interval is the beginning of ventricular depolarization all the way to the end of ventricular repolarization. Why is that segment important? Because if it's not allowed to proceed as normal, you can get an excitable rhythm, and then that can lead you into electricity on electricity. So basically, if this is too short, it can lead you into a ventricular tachycardia, ventricular fibrillation. All right? Just understand what the segment, what the waves mean. That'll be good enough for me in here. All right? And tomorrow, just so you know, tomorrow what we're going to do is we're going to talk about a full cardiac cycle. We're going to put together the innervation. Where does all this electricity come from? What is going on all at the same time? So it should wrap everything up nicely together in a little bit of a bow, all right? Because I've had the good question is, well, you're talking about electrical propagation. Where does it come from? It comes from a neural impulse. The heart is innervated. It's just we wanted to talk about today musculature so that you don't confuse nerves and propagation through a conductive myocyte, all right? So, if that last part doesn't make a whole lot of sense, this part helps tie it together, all right? Don't spend way too much time on the EKGs, but understand what the waves mean, understand what the segments mean, all right? It's not too difficult, especially as we put it together with next week, or not next week, tomorrow, okay? So if it doesn't make sense now, we'll go over it. We will go over it again tomorrow. We'll probably start back on EKG and work our way through the remainder of the material. All right? Does anybody have questions for me? Does anybody have any questions? I know it's difficult to formulate questions on the fly, especially when it's the kind of material we went over today. But do you see why I prefaced what I said at the beginning? Like it seems like a lot. Huge number of slides, but it's very repetitious. And so it's just the explanation followed by a picture, an explanation followed by a picture. So whatever way makes sense to you, if you watch the video and maybe that explanation makes more sense than my jumbled nonsense, then good, that's why I put them in there. And it's just another way to approach the problem. But as you start to look at it more and more, start to digest it, when you come up with questions, please fire away. Or you guys know where my office is, by the way? Good. Anyway, so yeah. So when we're at the lab, so if you go directly this way, that first door, 3107, is where we're going to do the lab on Friday. It's sort of like the lab morgue, and then 3106 is where I am. All right, so 31, you can just knock on the door, you can come through if it's open, or you can text me and see if I'm there. But that's where I'm at. All right. So if you have questions, once you start to really dig into it, just start firing away so that we can get those answered and cleared up earlier. But again, the nice thing about this schedule for us is that we have you, the royal we, have until next Friday to think about all this stuff. So, any questions for the end of the day? Awesome. See you guys.